I'm muted. It also starts to record automatically, just so you know. And you're also welcome to get the screen sharing going again whenever you're
all right. So, right, where do I share my screen? All right.
Should be a big green button down there towards the
Yeah,
bottom.
got it.
Awesome. Yep, I see it popped up now.
Mm-hmm.
Cool. So yeah, we'll wait a little longer.
All right.
And we'll get started. Okay. I think maybe I'll make the suggestion that we get going, because I see we've hit somewhat of a steady state at the moment, and then perhaps other people will join us. I'm sure with all the Zoom meetings going on these days, people have overlapping meetings in their calendar. So we'll get started. So welcome everyone. Good morning. Thank you very much for joining us today for this ECE colloquium. We're very excited to have Professor Asif Khan from Georgia Tech to speak today. And he's in the department or School of Electrical and Computer Engineering there. And the title of his talk will be Ferroelectricity and 21st Century Microelectronics. So a little bit about Professor Khan. He, as I mentioned, is a faculty in the School of Electrical and Computer Engineering, but also has a courtesy appointment in the School of Materials Science and Engineering. And I know that in the audience today, we have a few folks, not just from ECE, but also at MSc to reflect that overlapping or interdisciplinary focus of your research. His research is on ferroelectric materials, micro and nano electronic devices, based on those materials for advanced and beyond CMOS applications. And his early career work led to the first experimental proof of concept demonstration of a physical phenomenon, namely the negative capacitance or static local negative permittivity effect in ferroelectric materials, which can reduce the power dissipation in electronic devices below the fundamental thermodynamic limit. So this culminated in the initial development of the field of ferroelectric negative capacitance. And certainly there's been a lot of work that's been published in this area over the last few years, so big impact. He wrote the Semiconductor Industry Roadmap for Ferroelectric Memory Technologies in the 2018 edition of the IEEE International Roadmap for Devices and Systems, IRDS, and has also received a number of awards, including the Intel Rising Star Award in 2020, the Qualcomm Innovation Fellowship, TSMC Outstanding Student Research Award, and the University Gold Medal from Bangladesh University of Engineering and Technology. And he's also involved in a number of committees, such as the Technical Program Committee at IEDM, DRC, and DAC. So I think it promises to be a very interesting talk with a lot of great results, I'm sure. And I also want to encourage everyone to interact and ask questions. And as always, we have this Q&A function here at the bottom, and Michael and I will keep an eye on that. Asif, a quick question to you. Do you prefer for us to jump in and let you know when questions come in as they come in, or hold them all for the end of the talk?
I would appreciate if I mean, I would appreciate if you jump in and ask the question right away.
Okay, sounds good. We'll keep an eye on that and let you know. So yeah, take it away. We're looking forward to it. Thank you very much.
All right, thank you so much. Thank you so much for the generous introduction, and thank you so much for inviting me. to the ECE seminar, and I wish I could be there in person, and hopefully I will be there and see you all face to face. All right, so with that, let me get started. So I'm Asif Khan from Georgia Tech, and our group works on ferroelectric devices in general. So today I'm going to give you an overview of the type of work that we are doing in our group. But before that, let me first introduce to you Georgia Tech. This is Georgia Tech at the very heart of Atlanta. This is our Atlanta, or Atlanta skyline is amazing, and this is where Georgia Tech is. Please visit us. And the work that I'm going to present are done by these amazing individuals that are here in this photo, and this was taken before the pandemic started. So our group consists currently of 5 graduate students and 3 research engineers and postdocs. And thanks also to our sponsors, NSF, SRC, DARPA, and Intel, for all the enabling us to do all the interesting work. So with that, again, I am a big advocate of the area that I'm working on, and that is microelectronics. So let me tell you a few things about how I feel about microelectronics right now. And with that, I'll move on to specific topic that we are here. So what does microelectronics mean? So it means everything that has to do with the hardware that supports our information infrastructure, it supports our power infrastructure, and everything else. So again, just to give a very high level idea as to how I think about microelectronics, these 6.9 billion numbers on the background, in the front is actually Apple's Phil Schiller. He was presenting that 6.9 billion transistors are there in 2005 in iPhone 10. So the industry over the last 40 years has done an amazing job in putting in as many transistors on our pocket as there are people in the world. So, but these transistors are actually much more well-behaved than the people around us. They behave all the same. That's why our iPhones work. And what is the maximum number of transistors that we can get? To date, I believe the state of the art is 1.2 trillion transistor. And this is basically in this wafer that this gentleman is holding here. So this entire thing is actually a chip. And this chip is built for AI. So it can do amazing stuff. I don't think we have seen a demo of this chip working, but I'm pretty sure this will be an amazing chip. So the bottom line is that microelectronics is the basis of everything that is going to happen in the future. We know we hear a lot about AI, machine learning, so on and so forth, which are all amazing. But the things that AI and machine learning can enable will require a significant investment in microelectronics. What do I mean? From our smart car to healthcare, everything requires semiconductor chips. And it happens so that currently we are also in a region where we are in a shortage of semiconductor chips. For example, today's cars are actually like advanced cars, probably 50% of it goes towards electronics. And there was a chip shortage, and now a number of plants were closed. So the bottom line is, all of the revolutions that we're talking about, the fourth industrial revolution, IoT, and everything will require semiconductor chips. And currently the semiconductor chip industry is around $500 billion. And it is projected that by in 10 to 15 years, this can balloon up to $2 trillion and so on and so forth. So why am I saying this? Because there is a lot of discussion about the Moore's law scaling has ended. There is not much to do in the basic technologies that are powering these microelectronics, which are true, but there are a lot of innovations that can still happen and that are actually very much required. And on that note, because of many reasons beyond scaling, beyond the semiconductor need for semiconductor chips, geopolitics, so on and so forth, microelectronics is actually the one of the highest priority priorities for the Department of Defense and was actually designated a strategic national priority for US Congress. And the Chips for America has just recently passed, which is probably going to create a tsunami of investment in this microelectronics. So why am I bringing it up? It just means that as a research community, we need to keep on the innovation on the basic microelectronic technologies, as well as uh, training the semiconductor workforce to create the next generation of the technologists. So this is the reason I'm again saying it, is because this is something that excites me as an educator as well as researcher in this field. All right. So with that being said, what do our work on? Our group works on the basic transistor technology, but replacing one of the components of the transistor with a material called ferroelectric materials. So essentially, we work with the same transistor technology or whatever the technology will be in the coming nodes for advanced microprocessor chips, but trying to see if we can replace one of the layers that are in the gate oxide with a material called ferroelectrics. So why? Because it can bring new functionalities in the transistors for all aspects, from logic to memory to neuromorphic applications. So let me give you a quick overview of what a ferroelectric oxide is. So a ferroelectric is a crystalline material which may have a polar crystal structure like this. So if you are not very familiar with the crystallography, so I'll just ask you to focus on one of these atoms here, and that is at the center of this unit cell. So if you can see here, this atom over here is not at the center of symmetry, rather it's slightly off-centered. Now, this can be a positive or negatively charged ion, however you look at the crystal structure. And that would mean that since it's off-centered, at the unit cell level, this material will have a dipole moment. And the most important thing is that this atom can be in this position or off-centered from the center of symmetry by the same amount on the other side. So in these two cases, this unit cell will have an electric dipole moment in two opposite direction. And the other important thing is that by applying an electric field, you can switch the direction of the dipole moment. Now, these oxide materials are all insulators, so you can make a capacitor out of it. And if you make a capacitor out of it and measure the polarization or the charge on these metal plates as a function of voltage, what you will get is a hysteresis loop like this. So just for a comparison, if this material was not a ferroelectric material, rather a dielectric or a paraelectric material, the polarization versus voltage curve would have looked something like this, a linear curve. But a ferroelectric material has a hysteretic charge voltage characteristics. And if you look at the zero voltage over here, there are two states, one over here and one over here. That means that this material can work as a memory material, because even if you remove the voltage, it remembers whether the voltage went to a large positive voltage or large negative voltage. So that's that. So ferroelectric oxide is generally viewed as a material that can have a memory. All right. So with that, let's take a trip in the memory lane. So the thing is, ferroelectrics was first discovered in 1920. Actually, last year we celebrated the 100th year of discovery of ferroelectrics. Now, the most popular ferroelectric material has been the perovskite oxide materials. Now, you may have heard about perovskites in the solar cell context, but these are different classes of materials that the perovskite ferroelectrics are different than what we actually hear in the context of solar cells. So perovskite oxides were discovered to be ferroelectric in 1950s. And during 1990s and 1920s, semiconductor community was heavily interested in this type of ferroelectrics. And actually, there is a product that that came out of all the work that was done in 1990s and 2000s. And this was using a material called lead zirconate titanate and using it very low power memory devices that are used in smart cards. And the total market cap of this product is around $1 billion. But eventually, starting with 2000, the activity on ferroelectrics died down because perovskite materials are not compatible with mainstream semiconductor manufacturing, and it cannot be scaled down below 130 nanometers. So eventually by 2010, there was almost no activity on ferroelectrics on the semiconductor community. The material science and the physics community has been pushing the limits of ferroelectric materials, but in the microelectronics community, the activity almost died down by 2010. But again, as always, a surprise came in 2011, where ferroelectricity was discovered in Hafnia. So what is Hafnia? So if you have a state-of-the-art electronic gadget, for example, a phone or a laptop or computer, all of the transistors actually has a material hafnia as the gate dielectric in your transistor. So what the German group in 2011 reported was that if you take the same hafnia or an alloyed variant of this material and anneal it under certain conditions, this material becomes ferroelectric and also can become a sister phenomenon of ferroelectricity, anti-ferroelectric. Now, this really opened a completely new opportunity in the semiconductor industry, because with these materials, now you can use standard semiconductor manufacturing tools to make transistors, to introduce these ferroelectric materials in the mainstream highly scaled transistor technologies and any other technologies. And that has a very good chance of actually getting into high volume manufacturing. So that is exciting, and that essentially created a resurgent interest on all ferroelectric devices starting from 2011. So in last 10 years. So what I'm here showing is that all the different devices that can be enabled by the ferroelectric materials that was discovered. So on one hand, we have ferroelectric field effect transistors, where the ferroelectric is essentially being replacing the high K dielectric material in a standard logic transistor. Or you can have a ferroelectric capacitor that is connected to a front-end transistor over here that essentially works like a field effect transistor, but it has a metal in between. So the front end is a transistor, back end is a ferroelectric capacitor. Or the ferroelectric material can be on the back end, but same as this one, but connected to the drain of the front end transistor. This is called a ferroelectric random access memory. And altogether, you can also have the entire semiconductor field effect ferroelectric field effect transistor fabricated at the back end of the line, where the semiconductor and the ferroelectric both lies in the back end of the line. So here are many, many different variants of ferroelectric devices one can imagine. So now, why is ferroelectric field effect transistor so interesting? So there are many reasons as to why this is interesting, but the most important reason is that if you look at the energy profile of a ferroelectric field effect transistor, you will see that the energy per switching event is extremely small. It is 1 to 10 fem to joule. While if you compare it with an SRAM, this is really comparable. Now, all the other memory technologies that are out there, it is much more energy efficient than them. And area-wise, it's also efficient. So this is actually why the energy profile is why the ferroelectric field effect transistor is gaining a lot of attention lately. Okay, so with this introduction, let me now go into the work that we have been doing in our group. So our work is focused on two aspects. One is on the application level, what new kind of applications that ferroelectrics can enable. And then also the technology aspects, the device physics aspects of ferroelectric, the challenges of ferroelectric devices for integration into high volume manufacturing. This is another aspect that our group works on. So I will give one example from each of these areas that we are working on. All right. So now taking a step back, the computing paradigm. So to date, the computing paradigm has focused on von Neumann architecture, which makes a logical and physical separation between the computation and the logic, computation and the memory. Now, many of the data-centric computing applications driven by AI and machine learning can actually be done much more efficiently if the hardware itself has an architecture that does not subscribe to the von Neumann architecture. Rather, it has an architecture at the very fundamental level, which is non-von Neumann and potentially inspired by the way the brain works, otherwise called the neuromorphic systems. So we wanted to see if the ferroelectric can enable any of the non-von Neumann computing systems. So as a background, these are the conventional memory technologies, SRAM, DRAM, and the floating gate devices. They have all been used to enable different kind of non-von Neumann computing architectures. At the same time, we have different emerging technologies, for example, magnetic devices, phase change memory devices, resistive RAM, metal insulated transistor. All of these systems have also been used to investigated to understand whether they can enable non-von Neumann computing architectures. So to that end, let me give you a different perspective of ferroelectric field effect transistor. So if you think about a ferroelectric transistor, what properties does it have? It has hysteresis and non-volatility, it has plasticity, it has stochasticity, and it also has negative capacitance. Now, when I use this same ferroelectric material as the gate dielectric in a transistor, then we get a very broad range of functionalities that this device can enable. Because the transistor itself has a gain associated with it, voltage to current conversion gain. Essentially, this three-terminal device, the gain is essentially why it can enable so many things in computation. Now, when you add ferroelectricity, all these properties of ferroelectricity gets amplified because of the gain in it. At the same time, you have something called polymorphism, as well as, of course, it's a three-terminal device, so you can configure it in many ways in a circuit. So essentially, by combining the properties of the ferroelectrics with that of the transistor, you actually get a transistor technology, which arguably is one of the most versatile transistors that one can imagine. And essentially, this ferroelectric FET can enable different neuromorphic functions and non-von Neumann systems. So here I'm showing a number of examples of what these ferroelectric FET circuits, the neuromorphic systems, can enable. So I'll just talk about this first one, the coupled oscillatory systems. All right. So there has been of the different AI and machine learning paradigm, different approaches in AI and ML. One of the recent approaches is that of spiking neural networks. So spiking neural networks is sometimes referred to as the third generation of neural networks, the second generation being deep neural networks. So over the years, deep neural networks has been very successful, and it has led to many superhuman performances in terms of speech and image recognition, so on and so forth. But one of the things is that in terms of energy efficiency, the thoughts are that spiking neural networks can provide some additional benefits, maybe orders of magnitude more of benefits. The debate has not yet been settled, but there has been a lot of interest lately on the spiking neural networks. So what is spiking neural networks? The spiking neural networks is essentially a system where the information is coded in the temporal regime on the spikes. And if you, so one of the most celebrated papers on this field that came out not very many years ago is that if you think about a single SNN system, what you have is a plane of excitatory neuron and this plane of lateral inhibition neuron. So simply put, what happens is that once a signal comes in, and say, for example, that digit 8 is being recognized by this neuron over here, then what will happen is that the inhibitory neurons here will provide a signal to the other neurons not to fire. So what happens essentially is that once the system converges towards identifying a specific pattern, the inhibitory neuron networks provide a signal such that all other neurons are suppressed. So this is essentially the function of inhibitory neurons. Now, what is important is that to achieve efficiency in spiking neural networks, it is of utmost importance to have inhibition functionalities. So inhibition is extremely important for even in biological systems. For example, if we look at a simple neuron over here, many systems in the neuron actually need to have inhibition to activate the flow of information within our central nervous systems. And if we don't have it, then many neurodegenerative diseases actually occur. So there is a biological premise as well why we need inhibition in a spiking neural network systems. So, okay. So with that, why did we want to look at this? The reason we wanted to look at this is because we realized that if we have a ferroelectric field effect transistor, then the ferroelectric field effect transistor, due to its device physics, can already incorporate the inhibition within it. In other words, a neuron over here can be represented by a very simple two transistor circuit over here, where the inhibition naturally occurs because of the physics of the ferroelectric. So this is one of the interesting things. So I'll try to explain very quickly as to why the inhibition comes so efficiently in there, and then I'll show the advantages of it. But before that, how does a neuron or even an oscillator work? The way it works is that you have a hysteresis of the ferroelectric transistor over here. And then if you have a resistor and a capacitor network over here, and if you draw a load line over here, what will happen is that as long as this resistance is set such that it cuts through the two hysteresis over here, then the system will oscillate like this along this loop, and it will create this oscillation over here. But if you change this resistance over here such that this line no longer cuts through this hysteresis, it will stop oscillating as it's shown over here. Okay. So it essentially boils down to changing this value of this resistor to change the oscillation of the system. But what is interesting is that if you change this resistor with a transistor now, you can have the entire system. You can just control this oscillation with a second voltage over here. All right. So essentially, you can have this transistor over here to control the oscillation. But at the same time, the ferroelectric field effect transistor itself is a three-terminal device. So that means that you have a voltage knob over here. And this is very interesting as to what happens when we keep this voltage over here and change this voltage over here. So if we keep the voltage over here constant, then the system shows a hysteresis that looks like this. The hysteresis window looks like this. So although this looks like a simulation, this actually is an experimental curve of a ferroelectric field effect transistor. Now, if we change this voltage, what happens to the hysteresis is that the hysteresis width changes. So essentially, by changing this voltage over here, you can change the width of the hysteresis and essentially the oscillation in the system. Okay. So these are a lot of details. I'll not go into the details, but I'll just show you the main results. So we took a ferroelectric and a transistor and made a full ferroelectric spiking neuron over here. So let me show you the final characteristics. So what you see here over here is that these are the excitatory inputs. And these excitatory inputs are coming into this transistor over here. And when the excitatory input comes over here, you see that once it comes in, the potential or the synaptic potential starts building up, building up, building up. And suddenly, once it crosses a threshold, it starts spiking. So you get spikes like this. All right. So these are all excitatory input. And when the excitatory input was coming, the inhibitory input, meaning that the voltage over here was kept as a constant value at the base value. But then if you have another voltage that comes into here, then you clearly see that once it comes in, then it actually stops oscillating, meaning that the voltage level drops and then it starts oscillating over here. So that essentially means that the neuron was inhibited when the second input pulse comes in. Now, the bottom line is that all of this can be done in CMOS, but essentially here by two transistors, we are accomplishing what a CMOS transistor technology will require, I think, upwards of 32 transistors. So it's extremely area efficient in our implementation. All right. So now a little bit of comparison as to what our ferroelectric spiking neuron compares to other transistor technology, other implementations. So if you look at other transistor implementations, for example, here it takes 64 transistors to make it, or 15 transistor in standard CMOS. On the other hand, using metal insulator transition, you can do it 1 3 1, like just one transistor, one resistor. But among all of them, only our case can have both inhibition and excitation. And overall, the power is pretty low comparable to what you can have in CMOS, but much more energy area efficient. And so also by looking at a full unsupervised clustering on the MNIST database, we saw a 93% accuracy. 93% accuracy is not remarkable because with deep neural networks, you can do at probably 99.8% or 9% accuracy on MNIST database. But the important thing is that we are doing spiking neural networks and unsupervised clustering. So for this paradigm, this 93 number is actually pretty good. So, and because it's much more energy efficient. So that's kind of the benchmark that we did. All right, so at this point, let me talk just a little bit as to one of the areas one of my colleagues, Arijit Raichaudhuri, is very interested in, and we are collaborating and we are getting very nice, interesting results. So one of the things is that he is very interested is in coupled dynamical systems. So what does it mean? So the idea is actually inspired by the world of biology. So for example, if you look at ants, like bees or a school of fish, individually, each of these biological agents are not very intelligent, they're very simple. But when they're in a collective, when they interact collectively and behave as a collective entity, they seem to have a very strong intelligence. For example, the way a school of fish avoids a predator, or the way ant finds its way around the food, and so on and so forth, or the bees make decisions. All of these things are amazing. So this paradigm is usually called swarm intelligence. Even in our brain, there is evidence of synchronized or rhythmic responses within ensemble of neurons, which many neuroscientists think that they're related to things like perception, concepts, and so on, all these higher level ideas. So the bottom line is that using collective behavior in continuous time dynamical systems, you can probably solve computationally hard problems. So to that end, we did experiments, and then our colleague Arijit Raichaudhuri put these models into solving different computationally hard problems. So again, in the interest of time, what I'll just show is that we took our ferroelectric oscillators together and coupled them with the coupling capacitors. And by changing the coupling capacitors, changing this voltage, we can show that the voltage, output voltage of oscillator 1 and oscillator 2 can be coupled. For example, here we are showing a complex coupling between them. The thing is that all these paths are falling on top of each other, means that they are strongly coupled. On the other hand, in this case, for example, for a different voltage combinations, they're all the zigzag path, meaning that they're not coupled. So using these coupling mechanisms, you can solve a number of different computationally hard problems. For example, the Ant-Connolly algorithm to solve the TSP problem. If you drive the neuron in a mode that is called regular spiking, it can be solved very efficiently. More details are available in this paper. On the other hand, if you drive the ferroelectric oscillator or the neuron in a fast spiking mode, in that case, you can solve a convex optimization problem. So again, the thing is, I'm just going to, just wanted to show as to the power of this ferroelectric transistor technology in enabling new applications. Okay, so with that, in the remaining time, I'll just move on to our work on the technology aspects of ferroelectrics, and I'll specifically focus on understanding the microstructure of these materials. So first thing I'd like to say is that ferroelectric technologies, all of them are very exciting. But with any other new technologies out there, emerging technologies, there are many challenges. So for example, specific to the ferroelectric field effect transistors, there are 3 or 4 distinct challenges. First one is with respect to the right voltage and memory window. Second one is reliability. And the third one is device to device variation. So in the interest of time, I will just talk about the third challenge. And the challenge is as follows. So if I look at the advanced transistor technology node, for example, a FinFET node, the distance between the 2 fins are probably in the regime of 20 nanometer currently. And going forward, when we move to nanowire transistor technology, that gap might be even smaller. So that essentially means that the ferroelectric or the anti-ferroelectric layer can at best be 4 nanometer. We simply do not have any more space to accommodate a thicker film. So we need to have very robust ferroelectricity that is non-leaky, that is less than 4 nanometers thick. Second problem is that all of these materials, ferroelectricity is a structural phenomena, meaning that the material has to be crystalline. Now, how does the material actually crystallize on a 3D structure, or even it's possible to uniformly crystallized, whether it stays amorphous, crystalline, none of this information is not known right now. There are demonstrations of transistor properties, but at a large scale, high volume manufacturing, these are open questions still. So there needs to be a lot of fundamental studies as to understanding how the microstructure actually changes on a 3D structure of a advanced transistor technology node. So these are questions. Now, specific to this question that we mentioned in the earlier slide is that of polycrystallinity. So what does it mean? It means that whenever we have a ferroelectric layer on a transistor structure, it is sitting on an amorphous layer. So there is no epitaxial template that can make this layer as a single crystal. So essentially, it's a polycrystalline material. Now, in this ferroelectrics and anti-ferroelectrics, the typical grain size is of the order of 10 to 30 nanometers of geometric mean. And the range is probably 10 nanometer to 90 nanometers. And if I think about a normal, regular transistor, for example, 28 nanometer node transistor, probably has a length of 36 nanometer and a width of maybe some between 50 nanometers, 20 nanometers to 50 nanometers. So if I do the calculation, the number of grains that we can have in a transistor probably ranges between 20 to 100. Now, think of, for example, this is a 28 nanometer node with a channel length of probably 80 nanometers and width of 30 nanometers. Channel length of 30 nanometers and width of 100 nanometers. And within it, we have 8 grains. Now, having 8 grains in one device is a big problem. The reason is that all these grains are different in terms of phase, size, orientation, as well as there might be correlation between them. Now, if I have two devices sitting side by side, then this grain distribution might be very different between them. And as a result, their threshold voltages will be different and characteristics will be different. And we are talking about 1 billion or 10 billion transistors. And if there is this kind of variation between devices, then just because of variation, this technology will not work. So what needs to be done? Either we need to have a single epitaxial film, epitaxial-like film that is sitting on an amorphous substrate, or we need to make the grain size extremely small. So these are the two ends that needs to happen to make sure that this technology works. The thing is that it sounds very pessimistic, but actually a similar situation was there when first metal gate was introduced in transistor technology back in 2008. The metal gate was also polycrystalline, and this problem was solved by making the metal gate grain size extremely small as 2 nanometers or so. So these are the different problems that are there arising. And there is a solution that needs to happen to make it into a high volume, a technology that is in the high volume manufacturing. All right. So with that, let me show you some of our own work. So we have so far talked about ferroelectrics, but there is a cousin phenomena that is anti-ferroelectrics. And for some reason, we got very interested when we started our work in 2017 on anti-ferroelectrics. So anti-ferroelectrics is a first order phase transition between a non-polar phase and a polar phase. And without going into the physics of it, what it essentially means is that if you look at the hysteresis loop, there will be two hysteresis loop in the polarization versus electric field characteristics. And each of these transition here represents a phase transition, while in a ferroelectric, these are not phase transition, these are just rotation of the polarization vector. Okay, so the first thing that we did is we wanted to correlate the microstructure with the electrical characteristics. And one of my students, Nujat Tasneem, found a very interesting result that if you look at antiferroelectrics and scale them down, then the critical field for these phase transitions actually depends on the grain size, and it depends on the grain size raised to power negative 2/3. For example, if you look at here, the critical fields are linear function of d power negative 2/3. So that tells us that not only that it's a challenge, but the microstructure actually controls a lot of things within the material itself, with the electrical functional responses of the materials itself. So that was one of the interesting findings that we had in our group early on. So then we also did dark field TM imaging to find out the grain size distribution. Now, a common limitation that people usually say is that it's not representative. So what we did was we analyzed around 200 DFTM image to get a grain size distribution. And we saw that within 10 nanometer films, the smallest grain size, I believe, is around 4 nanometer, and the largest was something around above 90 nanometers here. So one of the small ones I don't see here, but I remember seeing one of the 4 nanometer size grains. So if I look at the grain size distribution over here, if I have a zirconia, it is a pretty broad peak with probably a geometric mean of, says around 23 nanometers. Okay, so it's probably here 23 nanometers. And some grains are pretty large over here. Okay. All right. So next thing is that one of my students, Sarah Lombardo, did a very cool experiments 2 years back in Oak Ridge National Lab. So what we did was that we took an antiferroelectric zirconia film and did a TM imaging of it with an in situ applied electric field. So what we essentially did was that we took it and we took the HRTM images of the zirconia layer. And while the voltage was applied, we were imaging it at the same time. So this is the zirconia, and we will particularly focus on this zirconia grain over here. So this is a quick overview of what is happening over here. So initially we have 3 domains within the grain. And as we increase the voltage, we see that the middle grain is changing. And finally, when we go to 4 volts, the middle grain completely goes away. But again, when we come back, we see that the middle grain starts to reappear, and finally we get back the original 3 domain structure. So I'll not take, so in the interest of time, I will just focus on one thing over here. And one of the interesting things that we saw is that when we look at a certain region of this domain here, we see that there is a line of atoms over here. When we apply 4 volts across it, we see another line appearing over here. So initially we have this line of atoms, then we have a second line of atoms appearing. And then when we go back to 0 volt over here again, this line of atom disappears. So that was a pretty interesting thing that we saw. So then we collaborated with our DFT colleagues who does DFT at UC San Diego and UT Dallas. And initially the 0 volt structure matches very well with the P4 to NMC tetragonal phase. But when we go to 4 volts, the additional atoms, we saw that it does not really match with any of the structures that we typically cite in our papers, for example, tetragonal P42NMC or PCA21 or PMN21. So our DFT colleagues found that it is somewhat of a match to a unusual, like not high, like not often reported phase of P4 to MNM. So that's what the thoughts were at that time, but this is not necessarily unique. But the fact that this structure was not uh, 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 matching up to any of the discussed structure was quite interesting. So the initial results were actually, this is published in VLSI 2020, but we're continuing to work more on to actually understand what's going on at the microscopic level. All right, so with that, I think I'm almost at the end of my time. So let me just summarize that there is a lot of excitement in ferroelectric materials devices. There are many fundamental aspects that needs to be understood. There are many technological bottlenecks, but and at the end, there are a lot of exciting things that these materials and the devices can enable. So, and overall, microelectronics is up for its fourth wave of revolution. So this is again very exciting time. So the work that we showed are in this more or less discussed in this paper. This paper not only talks about our own work, but the work of many of our colleagues, the very exciting work. We tried to summarize it, and we apologize if we missed any of the other people's work, but it was just to summarize all the activities that was going on in ferroelectric field effect transistor technology. With that, I thank you all, but I also thank all of my students and the sponsors. So with that, any questions? If there are, like to very much address all of this. And thanks again for being here.
Thank you very much, Asif. That was a fantastic presentation. And yes, we do have a question. One person asks, regarding negative capacitance, can ferroelectric devices be used to synthesize standalone negative capacitors?
So I guess what you are suggesting is, okay. So I believe the question is, so I believe the question is, you want a device which has a QV curve that looks like just like this, so that the capacitance is C. Unfortunately, you cannot, so at least for the ferroelectric devices, we cannot have a ferroelectric that shows a large signal negative capacitance in a standalone fashion. So if we want to buy for example, we can buy ceramic capacitors. If I want a ceramic capacitor that gives a negative C between these terminals, that cannot be achieved with a ferroelectric because the ferroelectric is an unstable. But what we need to do, so the way it works in a transistor is that in a transistor, we have a positive capacitance in series with it. So if I have two capacitors in series, what it will do is that, so in general, if we have two capacitors in series, the total capacitance is smaller than both of them. But if I put a negative capacitor in series with a positive capacitor, the total capacitance is actually becomes larger than the positive capacitor. And for a transistor, this is very important because that can reduce the subthreshold swing, it can increase the on current and so on and so forth. So that's why negative capacitance idea was proposed for that's why ferroelectric negative capacitance idea is very useful for a transistor or even DRAM applications or any applications where you want to have a larger capacitance for a given area. But that being said, it would have been nice if we could have a capacitor that looks like this, that is just negative between two terminals. But we think that nature does not permit to have it. But if it permitted, that would have been so wonderful, because you could have canceled any capacitors by adding it to a normal capacitor. But yeah, the answer is that with ferroelectrics, we cannot do it.
Great, thank you. Another question just popped in. So this question is related to mass manufacturing. How does the cost per unit compare to traditional FETs used in microprocessing chips? For example, does the material or technology cost twice as much as the current technology?
So this is a very, very good question. And as you know that for any technologies, cost is finally the deciding factor. So I would answer it like this. So for example, if I think about, okay, where is my picture of this thing? So first of all, the material cost is minimal because hafnia, zirconia, all of these things are already in mass manufacturing. Hafnia doped with something is already in all our transistors in electronic gadgets. Zirconia is in on all our DRAM products. So material know-how is there. Now, usually the reason cost increases in a transistor technology is usually mask. So to make a ferrofet, you need two additional masks. And the thing is, so for ferroelectric, you need two masks, extra masks. But you know that in E-flash, how many masks that is needed? It's probably extra 5 to 7 masks that are required. For spin devices, I believe it's something of the order of 10 masks additions. So from a cost perspective, ferrofet is actually very cheap, meaning that it is within all the technologies that are out there, emerging technologies. Ferrofet is the cheapest one because it requires least amount of additional masks.
Gotcha.
The other thing is that current technology none of the current technologies can you give the energy profile that a ferrofet can give. For example, look at all of these things like non-volatile memories. These are extremely high energy. Ferroelectric, because it's a voltage driven or electric field effect, it's very low energy. So there is an order of magnitude advantage of using ferroelectrics, provided we can solve the problems.
I have a follow-up question to this in terms of how it fits into current technology. So are there any differences in terms of how one deposits the material, whether you do it through ALD or PLD? And then, based on the differences, if there are any in the deposition method, how that then is compatible or not as compatible with the current mass production technology that's out there?
Right. So it's exactly same tools that are used. Even the precursors are the same. So I believe, okay, so all the industries have their secret recipes, but we work very closely with the industry. For example, we receive a lot of samples from the industry themselves, and they're exactly using their own, like the same precursor they use for the we are working with the tool manufacturers, and they do supply the tools to the IDMs, and the exact same tools they are providing us the material, and those materials turn out to be very robustly ferroelectric or anti-ferroelectric. So it's just a matter of one anneal that we need to do, something around 450 degrees Celsius. So it's like seamless integration. But the problem, of course, there are many prop challenges, device physics challenges that needs to be solved. But tool-wise, incorporation-wise, there is no challenge.
Okay, gotcha. I have another follow-up question, which involves the types of devices that you can integrate these materials with. So you gave a lot of very good examples of neuromorphic computing and I guess computing in general and the advantages in terms of energy consumption. But I wonder, are there other devices, for example, power devices, high frequency RF devices, where negative capacitance could be leveraged to improve speed or again reduce power consumption? Do you have any perspectives on that? Especially going away from silicon, if you try to do this with 3.5s or something like that.
So first of all, there are definitely advantages of, and of course, the negative capacitance is very interesting from an RF perspective. So I believe there are a lot of ongoing efforts on integrating ferroelectrics, anti-ferroelectrics, and negative capacitance materials on 3.5 platforms. 3.5 meaning high mobility, no, 3.5 platforms. So there are definitely a lot of advantages to doing it, but I don't think the results are clear yet. Whether you can get an advantage in RF domain. On the power domain, I don't know what the advantage will be, because in power domain, I think that the subthreshold swing is not a problem. You don't need memory, probably not a very good need for memory devices with power devices. But I don't think there has been a lot of work on power devices using ferroelectrics or anti-ferroelectrics, although I know a number of people who are trying to work on that.
Gotcha. Yeah, the other one I can think of is perhaps even sensors, chemical sensors, for example, ISFETs, where subthreshold swing could perhaps be an important part of the performance.
Yeah, so I haven't thought about sensors.
Interesting. Yeah, just checking the question. So yeah, feel free to enter any other questions. Maybe I'll ask one more just in case something else comes in the meantime. Going to the topic of manufacturability and this idea of scaling and being able to achieve reliable performance, I guess I was just curious what the main knob is. Then I wasn't 100% clear to me. It wasn't clear to me what the main knob is to achieve that small grain size. Is it going to be thickness scaling, or is it a change in stoichiometry? What is the main knob that you think is the most promising to be able to solve this problem? And is it similar to the knob that they use to deal with the introduction of a metallic gate? I mean, is it going to be a completely different approach, or are there similarities there that that can be adopted?
So yeah, that's a very good question, and this is an open question. I don't think anyone knows the answer to, but the main thing is that whenever so most of the work has been limited between 5 nanometer and 10 nanometer of thickness, and it's an empirical observation that below 4 nanometer there is a significant change in the microstructure that happens below 4 nanometer, and basically any material below 3 nanometers, crystallizing them is really hard. For some reason, it just wants to be amorphous. It's not that you cannot do it, but the techniques that we use to crystallize it 5 nanometer does not work at 2 nanometer. Either we need to increase the temperature, increase or decrease the annealing time. That change needs to change the ambient gases that are present when crystallizing, and most importantly, so this is the gate metal stack, and this gate metal stack needs to be changed as well to crystallize this thing. So it's more like a problem where we need to look at the entire system as a whole, holistically. Like, we need to see what is the interlayer that is underneath the ferroelectric layer, what is the metal layer, what is the annealing temperature we can apply, how long, whether we can do some sort of other types of flash annealing and stuff. So these are all the questions that needs to be addressed. So right now I don't think there is a right answer to how we can make it robustly ferroelectric at 2 or 3 nanometers.
Gotcha. Okay, great. Well, thank you very much. I don't see any further questions that have come in through the chat there. So I think we will wrap up here. I do appreciate the presentation, very interesting, and I think it's really cool to also see the way you've taken this from the fundamentals of the materials and the device, just demonstrating that there's negative capacitance all the way up now to applications, and showing how you can make some of these multi-transistor circuits, and demonstrating how neuromorphic computing would work from there. So thank you for tying all that together and giving us that perspective. It's very interesting.
All right. Thank you so much. And thank you so much, everyone, for attending.
Absolutely. Thanks again, and have a good weekend. And Asif, I hope we'll be able to host you here in person one day and show you around Raleigh and NC State.
All right. Yeah, looking forward to that. And same to you for Atlanta. I mean, you are from here, so yeah.
Yeah. I enjoyed seeing that picture at the beginning. Fantastic. Thanks again. Have a good one.